Now, particle in sphere, in a sphere. In this problem, we deal with a particle that can move easily inside a sphere, but not outside, because there is infinite potential outside of the sphere of radius a. And then the wave function is given by the formula, which should in general be depends on theta and r and phi. So psi theta r phi, which is but here there is a cosine b r over a. The formula in the blue box, and this formula there is no functionality on theta and phi. There is just functionality on r. Now what does that mean? That means something which we call this symmetry of central symmetry. Central symmetry, which we will get benefit of it later. The first question now, compute the normalization constant. The normalization constant, that means we need to take the amplitude of the wave function square, which is represent probability of finding the particle somewhere. The probability of finding particle inside, because it is infinite potential outside, because so it's 1 inside the sphere. I am sure that the particle inside this sphere. So make the integration. The integration is easy for the because there is symmetry on theta and phi. There is no dependence on theta and phi. So the integration will give you just the factor of 4 pi. And the integration over r, because the infinitesimal dr cube, the infinitesimal volume of in spherical coordinate is given by r squared dr d theta d phi. So I have r squared dr, and also there is functionality over r inside the wave function. So I have this nasty integration between a and r squared cosine squared br over br over a dr. I call it e, and this is not we use trick in order to calculate it. What is the trick here? We make the constant p over r. I call it p, for example, pi over r. I call pi over a. I call it p, and I make this constant variation of this constant. So that means. And now, why I use this trick? Because if I make now the twice derivation with respect to this constant, I will give the first time minus cosine p minus r cosine pr. The second time it will give other r, so r square minus r square cosine br. The first is minus r sine, the second minus r square cosine. I inject it inside this integration. I call it e, and I found that I make minus d square over dp square of the integration of the easy function, which is just cosine br dr, which is just sine between 0 and r and a, and because sinus 0 is 0, I will get this formula. Sinus pa over p. I make twice derivation with taking into consideration there is minus the twice derivation. I get the result here, and now I use the fact that I put p is b equal pi over a, and so every sign will be going to 0, because it will give you sine pi, which is 0 firstly. I have just two terms. By calculation, it will give you just a cube over pi square. So this is equal to 4 pi a capital square. So the a capital, which is the constant of the normalization constant, it will give you 1/2 a over pi 3 over 2 to the power 3 over 2. The second part of the problem is what are the possible results of the measurement of the energy of each particle, and what are the possibility of obtaining each of them. Here we are dealing with particle freely move inside a sphere, and there is infinite potential outside, so it cannot be escaped from the sphere. So the probability of finding this, the particle inside the sphere, somewhere inside, is equal to 1, or the sum over all the probabilities are equal to 1, as we use this fact to calculate the normalization constant. But here he asks about the energy of the particle and the outcome of the possible outcome of the measurement of the energy. The possible value of the energy is the eigenvalue of the Hamiltonian, which is given by b squared over 2m plus Vr. To solve the problem, we use the radius-Schrödinger equation, which is minus h bar over 2m d squared over dr ur plus h bar over 2m l plus multiplied by l plus 1 over 2 over r square ur, which is equal to eur. And here we use the spherical symmetry because there is no dependence on the wave function on theta and phi, and there is only dependence on r. The non-trivial case just when L equals 0. So the second term in the equation will vanish, and I will get normal or easy to solve differential equation, which is minus h bar over 2m d square over dr square ur plus 2em over h bar square ur. And this equation is the solution of it is linear of combination of sine and cosine. But here we will vanish, every cosine will vanish. Why? Because we know that ur should vanish at center when r equals 0. So I have just sine, an multiplied by sine. How I can calculate en? I can calculate en easily by just taking also normalization constant, which is en. I make integration equal to 1 over all the sphere between 0 and r, and finally I will get en equal to square root of 2 over a, small a. The eigenfunction could be written. The eigenfunction are the base of or the wave function could be written in terms of the eigenfunction as the following: the sum over n cn cn. Cn, the amplitude square of the Cn is the probability of measuring the energy En, and the wave function, the eigenwave function will be written as Rn multiplied by y delta phi. So it's multiplication of two terms. The first depends on Tr and the second depends on theta and phi. Since we have symmetry also, spherical symmetry, there is no dependence on theta and phi, and we will put y theta and phi will be equal to just 1 over square root of 4 pi. And r is given as a function of ur, which is calculated previously, is ur over r. And taking that normalization constant En is equal to the square root of 2 over a, I finally found Cn. Now, we return back again to the coefficient Cn. Cn using Dirac notation will be equal to Cn bracket of Cn psi. So Cn psi, and I found the eigenwave function, which is Cn. I found it previously, which is given by the constant a prime. For example, a prime, I call it a prime equal a to En, which is equal to 1 over square root of 2 pi multiplied by a over pi to power 2. And Cn, so it will be given by this formula here. Now this bracket, I call it E prime, or I call it whatever, and this bracket is the integration of the complex conjugate of Cn, which is the same because it's real, multiplied by psi, which is given by in the problem. So it's multiplication of some constant multiplied by r squared, because the infinitesimal volume is r squared dr d theta d phi, over r multiplied by sinus pi n r over a, b multiplied by cosine b r over a. So now I have Cn equals some constant 4 pi a prime to the square root of 4 pi, and I get 4 pi because also there is spherical symmetry. There is no the integration over theta and phi, it will give you just 4 pi. And I take another integration which is depends on r, and it is a bit nasty and complicated, and I will use another trick in order to calculate it. The trick is to put the cosine by r over a, where there is no n. I make the constant pi over a variated. I call it p, and then I will get r in order to solve it. I will get r by just first derivation of it. And now e, I call it this integration is e, by putting p equal pi over a, and we inject it inside the cosine, and I will make first derivation of cosine. It will give a rise to r. So d over dr integration of between 0 and a to of sine br sine ln by r over a dr. This integration is easily to solve just by remembering that sinus x sine x is equal e to power ix minus e minus ix over 2i. I have the multiplication of 2 sine and sine, so I have 2 terms of something like that. After injecting it and after some calculation, we re-inject p is equal pi over a. So all the term where is sine will vanish, and all the term where is cosine will give you some constant, and finally the e will be equal to e. It is e is the name of the integration, and maybe I must use another letter in order to recognize it between inertia and e, the integration. So here e, the integration, is will be a number, and this number is minus half a square over pi n plus 1 minus a square over pi 1 minus n. I can reorganize it because it is just multiplication of constant. It will give you Cn. In this way, we will find the probability of finding, and this probability of Cn, the amplitude of it should be forcefully smaller than 1, because the sum over the square root of the amplitude of all Cn, it should be equal to 1, or the sum, maybe it's integration.